Okay. Welcome all to the week 11 of Advanced Concrete Technology. So, in the previous week, we learned more about the durability problems and the different specifications we need to figure out or we need to provide for ensuring that the concrete is strong and as well as durable. So, these were the certain concepts which we covered the last week. So, without further ado, let me move to the presentation with the questions. Yes. Is my screen visible to all?
Yeah, man.
Okay. So again, it's about the week 11 topics. So let's move to the first question. Yeah. First question is the paste and aggregate expands during dash. So concrete is composed of paste, aggregates, that is fine aggregates and coarse aggregates. So, during what process does the paste and the aggregate expands? Let me adjust the screen. Yeah, I hope that's okay. Let me post the question in the chat box as well. Okay. So, I again repeat the question. The paste as well as the aggregate expands during alkali silica reaction, corrosion, freezing, and sulfate attack. Okay, so thank you guys for responding. Yeah, I can see about ASR freezing, about yeah, again ASR freezing. Excuse me. Okay, okay. Should I wait for the others to reply? Okay, I'll give a few more seconds. Okay, so we'll deal in detail about alkali silica reaction, corrosion, freezing, and sulfate attack in the following coming sessions. But in general, what makes the paste and aggregate expand? Okay, so clearly, in the case of corrosion, it mainly attacks the reinforced cement concrete. It attacks the reinforcement, and it can be either carbonation induced corrosion or chloride induced corrosion. So the corrosion product has a six times of volume as that of the original product. So that is an expansion, but that happens only in the steel phase, not on the concrete. So here the question is about paste and aggregate. So clearly B is not an answer. So is it A, C, or D, or both A and C, or C and D? That is a question. Okay, let's move to the answer. I hope that's all. That's all the replies I'm getting. Okay, so the correct answer is freezing. It's not alkali silica reaction. It is freezing. Why? Because in alkali silica reaction, it's because of the presence of siliceous aggregates, and it expands the aggregate, not the paste. So alkali silica reaction expands the aggregate, not the paste. So the question is paste and aggregate has to expand. So it's not alkali silica reaction. Then corrosion, it expands the steel. Then freezing, because when the water gets into the concrete pores and undergoes freezing, when it becomes ice, there will be a volumetric expansion, and that can happen in paste as well as aggregate, causing the paste and aggregate to expand. So the correct answer is freezing. Now, why is it not sulfate
Isn't it
attack?
contradictory, man?
Sorry?
Isn't it contradictory? Because alkali silica reaction, you are telling that it expands the aggregate.
Yes.
If aggregates are expanding, that means it is pushing the paste also. That means volume is increasing there also.
No. Paste is being pushed away doesn't mean that it is expanding, right?
But
Suppose,
the aggregates are expanding, है ना ma'am, in ASR.
see, suppose this is a paste. Okay, this is an aggregate. In ASR, aggregate is expanding and it pushes away the paste. Does this mean
And
that the paste is expanding?
it is not expanding, but the same case is freezing also, ma'am. Freezing, it is just expanding the volume. It is not the paste oblique the aggregate which is expanding. It is the volume which is expanding. It is like pushing away. Like you said, the aggregate is pushing the paste away.
Yes,
The freezing, the water grade freezes, and once it becomes solid ice, so it is again
yes.
pushing the paste and the aggregate.
So the
There is no
entire
expand.
volume of the paste and the entire volume of the aggregate increases.
Ma'am, but ASR also is the same, doing the same thing. And ma'am, it is also pushing aggregate is the one component is expanding and it is pushing the paste.
It just pushes away. The paste is not being. See, whenever there is a water within the paste, it expands. The paste correspondingly it expands. It is not cracking until it reaches the tensile strength. It is
Okay, ma'am.
correspondingly
Now,
expanding along with the
sorry, ma'am.
mix.
In between, I'm interrupting you.
Yeah.
You are at the right point. What you're telling now, the water which is in the paste,
Yes.
it solidifies the
Yes.
water and it expands the paste.
Yes.
But in this case, the aggregate is not expanding in freezing. Aggregate is same. The composition or the size of the aggregate is the same thing. It is vice versa. In alkali ASR, the aggregate is increasing and pushing the paste,
Hmm.
whereas in freezing, the water is solidifying. It is increasing the paste and pushing the aggregate.
It. Yes, sir. You rightly told it pushes the aggregate. It is not expanding the aggregate.
So, ma'am, the question is the paste and aggregate expands. Both should expand.
Yes.
But in freezing, nothing is happening to the aggregate, ma'am. It is of the same size.
No. When there are water droplets within the aggregate, and then the water converts into ice, it is obviously expanding.
That is the paste will expand, ma'am, not the aggregate.
Aggregate
Aggregate is
also.
inert material. With the water, with the aggregate, will it expand, ma'am?
Yes.
Aggregate a stone. If I take a stone and put it in a freezer, will it increase in volume, ma'am?
I mean, the water increases in volume, so which results in the expansion of the aggregate.
Okay, ma'am.
Yeah. So the correct answer is C, which is freezing, because it expands the paste and the aggregate. Not A, because it expands only the aggregate and not the paste. So moving on to the next question. The pore size obtained through MIP that indicates maximum volume intrusion is dash. So the question is mercury intrusion porosimetry is MIP, and during the test of MIP, we get different parameters. So, what is that parameter which indicates maximum volume intrusion? Is it the threshold pore size, or is it the critical pore size, or is it the differential pore volume? We get different parameters through MIP testing. And what is that parameter which indicates a maximum volume intrusion or the maximum size at which there is a higher percentage of pores, or the pore size at which there is a maximum volume intrusion of mercury? Okay, there is only one response. Should I wait for some more time? Okay. So I'm just going into the answer. I guess that is only response I'm getting for this question. Okay. So the correct answer is critical pore size. So this is one typical graph which we can obtain through MIP. So if you see, there is a differential pore volume graph. If in this graph, you can see that the intrusion volume is in the differential intrusion volume is in the y-axis and the pore dia is in the x-axis. So there is a higher intrusion volume peak you can see here, and the corresponding diameter of the pore indicates that at this pore size there is a maximum intrusion of mercury. So that point is known as a critical pore size. So the correct answer is critical pore size. It is a pore size indicating the maximum volume intrusion of mercury in MIP. Now, moving on to the next question. Consider the Kozny equation connecting the porosity and permeability. So there is this term S here. The S for a sphere of radius r is dash. So Kozny equation connects permeability and porosity. The S for a sphere of radius r is dash 3r, 3 by r, 1.5 r, or 4 by 3 r. For this, first of all, you need to know the Kozny equation. It is given here. Secondly, what you need to know what is a S. Okay, thank you, Shrish, KPC Rao, and BCS Reddy. So the three responses, three of them are saying it's the option B. Okay, I'll wait for a few more seconds. Okay, I hope those who can reply have already replied, or is there anyone else who wish to answer? So porosity and permeability are related by using the Kozny equation, and there's a term S in that. So what is S for a sphere of radius r is the question. So here goes the answer. The correct answer is B, as all of you have rightly told. So from here you can see that permeability and porosity. This is a screenshot from the same slides. So here S, what is S? S is the volume specific surface area of the particle, which means that surface area per unit volume. So surface area of a sphere is 4 pi r square, and the volume of a sphere is 4 by 3 pi r cube. So S for a sphere is 4 pi r square divided by 4 by 3 pi r cube. So 4 pi r square divided by 4 by 3 pi r cube. This will give the answer as 3 by r. Okay. So the area by volume is S. Area is 4 pi r square. Volume is 4 by 3 pi r cube. 4 pi r square by 4 by 3 pi r cube. 3 will go into the numerator and 1 r will be there in the denominator. So the correct answer is B, that is 3 by r. Okay. I hope that is clear. Now let's move to the next question. Mentioning the water sorptivity is an example of prescriptive specification. Is it a true statement or a wrong statement? Say true or false is a question. So, mentioning the water sorptivity. So, finally, after construction, maybe you have to mention the water sorptivity of the particular concrete. So, is that a prescriptive specification? Is the question. I mean, that is a prescriptive specification is a statement. Is that a true statement or a false statement? Okay, I've got just one response. Mm, Kandasamy, why have you raised a hand? If you have any question, please feel free to unmute or yeah,
Yes, ma'am.
yeah,
Ma'am, are you? Am I audible, madam?
yes,
Am I audible?
yes.
Ma'am, yesterday I asked one question, madam. Yesterday I asked one question to the another madam regarding the question from week 8, madam.
That is penetrometer and the what it was workability about the workability question, no?
Workability is regarding workability.
Ah,
I think the answer is slump code,
slum cone, yes. So I was about to
but
discuss
the
this in
answer is
the this session. Yeah. So I have changed that. It was a mistake because in the video also it was told penetrometer, but we discussed with the professor. So in a global sense, it is actually slump cone. So I have edited that in the PDF which
okay,
is uploaded, and slum cone will be the right answer.
okay, okay,
Okay. I hope that's clarified.
okay. Thank you
Yeah.
very much. Thank you.
Fine.
Yes, ma'am. Thank you.
So, yeah, coming back to our session, the mentioning of what is optivity is an example of prescriptive specification was a question, whether it's a true statement or a false statement. So here I can see that I received four responses, four of them goes for false. Yes. So the correct answer is false. Why? Because it is a performance based specification. So clearly there are two types of specifications. One is prescriptive specification, the other one is performance based specification. So prescriptive, as the name suggests, it is prescribing what should be done or what need to be used, like you have to use this much of cement content, or the maximum cement content has to be this much, or the water to binder ratio has to be this much. So prescribing what need to be used or what must be the condition. On the contrary, if you go for performance based specification, it focuses on the final output or the performance of the final output. As such, in this case, what is the water sorptivity of the um, mix, or the water sorptivity of the specimen after so and so days? That is a performance, like how the final output performs at the end. So it is a performance based specification. It is not prescriptive, it is a performance based specification. Now, moving on to the next question. So, Dash gives the opportunity to use SCMs and innovative additives in concrete mix design. So, is it the prescriptive specifications or the performance based specifications which provides an opportunity to use SCMs and some other innovative additives in concrete mix design? Yeah, this is a very easy question. So, I don't think there's nothing much to think about in answering. This is a fairly easy question because when we are going for prescriptive specifications, then it will have clear cut instructions what to use, what not to use. So there is a limitation for a concrete mix designer or the engineer to use some local additives or some other SCMs from the sustainability point of view, which must be giving better or even equal performance as that of the normal concrete mix. Suppose we are going with performance based specifications, we are focusing on the final output or how the concrete specimen behaves finally. We are not focused on what need to be added to the mix instead. So that gives us more freedom to use, say, more SCMs, or suppose, say, there are some locally available materials which is a waste material which we can use in the concrete, can give a better performance or the adequate performance. So it performance based specifications gives us that freedom or that opportunity to use new materials or innovative materials. So the correct answer is B. So it gives us the freedom to use the consequences, and the end product quality is what matters. It's not the first stage addition of raw materials what matters. So that is why performance based specifications gives the opportunity to use SCMs and innovative additives in concrete mix design is the correct statement. Okay. So, moving on to the next question. Suppose there is a concrete specimen which is kept underwater for an extended period of time. Okay, such that the pores are filled with water. Now, dash diffusion is likely to happen in this concrete. Suppose there is a concrete specimen, it is kept underwater for an extended period of time. So, to make the point clear, it is given that the pores are filled with water. Now, what diffusion is likely to happen in this concrete? Gaseous diffusion or ionic diffusion? Okay. Thanks for responding. Yeah. Let's wait for a few more seconds, maybe. Okay, so let's move to the correct answer. Correct one is ionic, as all of you have rightly told. So for the gaseous diffusion to happen, it should happen through unsaturated concrete. Whereas in the case of partially saturated or fully saturated concrete, ionic diffusion can happen. So the gas to pass through, it shouldn't be saturated. But if it is saturated, which means the pores are fully filled with water, as in this case, ionic diffusion can happen. Okay, so moving on to the next question. Okay, so this is also a true or false statement. Fick's first law of diffusion is applicable to concrete specimens. So this is a very general statement. Excuse me. Okay, there is a concrete specimen. Fick's first law of diffusion is applicable. Okay, I'm getting Shrish, KPC, Niklesh. Okay, Niklesh, I think you now joined. Venkatesh. Okay. So, Niklesh, can you explain or can you justify why you went with false? Why Fick's first law cannot be applied to concrete specimens? Niklesh, are you there? Can you unmute if possible? Or you can even put it in the chat box. Venkatesh, are you there? Okay, okay, Niklesh, no problem. But can you put in the chat box why it was false? You're telling Fick's first law of diffusion cannot be applied to concrete specimens. I'm asking why. Is Leah in the meeting? Leah? No. BC is ready?
Just now I read, madam, 1 hour back. So with memory, I put it.
Okay, so do you remember like why it is not applicable?
I have no clarity.
Okay, let's move to the answer then. So, correct answer is false. But why we cannot apply is because fixed first law of diffusion is applicable only for steady state conditions. So steady state meaning with the progression of time, the properties of that material shouldn't change. So that should be the steady state condition. But if you consider concrete specimen, we already told that hydration is a ever prolonging process, and obviously as the hydration progresses, the concrete properties are continuously changing. So it's not a steady state, it's always an unsteady state. So in that cases, as the concrete properties are changing, keep on changing over time, like its strength is evolving, porosity is evolving, permeability is evolving. So in that case, it is not a steady state. Because of this, fixed first law of diffusion cannot be applied. First law is KP0. First law is for steady state and second law is for non-steady state. Second law more appropriate for ionic diffusion through concrete as microstructure is evolving with time. Yes, perfect. So as I rightly told, the microstructure, the strength, the porosity, permeability, everything is evolving over time for concrete specimens. Because of that, it is an unsteady state. It is not a steady state. And fixed first law of diffusion is applicable only for steady state, not for unsteady state. So we cannot apply fixed first law of diffusion to concrete specimens. Okay. Thank you all for responding. Now moving on to the next question. Yeah. This is also related to the previous question, which is very easy. The diffusion coefficient used in the calculations concerning concrete specimens is true diffusion coefficient or apparent diffusion coefficient. So this is also related to the point which we are discussing right now. So is it the true diffusion coefficient or is it an apparent diffusion coefficient? Okay. Okay, I think answers are coming. I got 4 responses. Shall we move to the correct answer? Yes. Correct answer is B. Why? Because true diffusion coefficient has to be a constant, but in the case of concrete, it is not like that. Microstructure is evolving over time. As a result, the diffusion coefficient is also not a particular constant and it is also changing. It varies over time. So we have to take something like an apparent diffusion coefficient. So moving on to the next question. Yes. The relationship of carbonation depth and time in an accelerated carbonation setup is linear, it's horizontal, which is parallel to time axis, quadratic, then linear initially, and then parallel to the depth axis. Sorry, this is not x axis, parallel to depth axis. So, carbonation is a natural process. Carbon dioxide will get into the porous media of concrete and it undergoes carbonation. It depends upon whether we are keeping it in a natural atmosphere or in an accelerated atmosphere. We can even put it in an accelerated carbonation chamber to increase the rate of carbonation of concrete so that it is more convenient to study in a laboratory setup. We can accelerate the process. So, in that kind of a setup, if we are going for accelerated carbonation of concrete, then obviously we can plot at particular time this much depth of carbonation occurred. At particular time, this is the penetration depth of the carbon dioxide into the concrete. So, the question is about that graph or that relationship, the depth versus time. Usually, the time will be in the x axis and depth will be in the y axis. So if you plot the depth versus time or time versus depth, then what will the relationship be? Is it a linear relationship or is it horizontal, that is parallel to the time axis? Or is it linear initially, then parallel to the depth axis? Then, or else it is quadratic. So this is about the accelerated carbonation test setup and the relationship between the carbonation depth and the time. I guess that was enough time to think, right? Okay, should I wait for some more seconds? Only three responses till now. Okay, four. Good. What about others? There are like nine participants. Five more yet to respond. Don't worry if your answer goes wrong. Just consider this as a learning platform. Okay, let's move to the correct answer. The correct answer is C, which is quadratic. Because since we are accelerating the process of carbonation and because of the heterogeneity of the concrete, it is not like within 5 minutes, suppose it is 1 mm depth, in the 10 minutes it will be 2 mm depth. No, that will not happen. It will actually be fast initially and then gradually it will become a steady state. So it is kind of a quadratic relationship between the depth and the time axis. So when you told linear, that is correct, but that is in the d versus root t graph. If we are plotting it with root t, it is a linear graph, but with time, it is a quadratic graph. I hope that is clear. So, moving on to the next question, which is also related to the same. So, carbonation rate or the rate at which the carbonation or the carbon dioxide penetrates into the concrete is very important because nowadays there are many modeling softwares which can model the service life of concrete. For that, we need carbonation rate. So, that carbonation rate is the slope of dash graph where d is the depth of penetration and t is the time. So is it d versus t graph or is it d versus t square graph or d square versus t graph or d versus root t graph? Generally, the depth is mentioned in the y-axis and time is mentioned in the x-axis. So is it d versus t graph which gives a slope equivalent to the carbonation rate, or is it d versus t square graph which gives a slope equivalent to carbonation rate, or is it d square versus t graph, or is it d versus root t graph? I'll put it in the chat box also. So d versus t, d versus t square, d square versus t, and d versus root t. So slope of one of this graph gives a carbonation rate. Let's move to the answer then. I guess yes, we can move to the answer. What about the others? Nikhilesh, Venkatesh. Okay, no worries. Let's move to the answer. The correct answer is D. So this is just a screenshot because this was not a graph which was already present in the slide. Professor drew the graph, so I just kept the screenshot just for your reference. So there was this slide of accelerated carbonation test and he drew that D versus root T graph gave a linear relationship whose slope gives the carbonation rate. So if you have any doubt, please go back and check this particular slide. So this is it. D versus root T graph gives a slope which is equal to the carbonation rate in concrete specimens. Okay. So moving on to the next one. Choose the methods which can be used to ensure better penetration of water into concrete. If at all you want more water to get into the concrete, so what are the methods which we can use to ensure better penetration of water into concrete? Option A, increasing the surface tension of water. Option B, boiling the water. Option C, keeping water and concrete under vacuum. And all of the above. If you want to saturate the concrete much faster rate, what will you do? Okay. D, A. Thank you for responding. Others? D. Okay. Okay. All are going for D except one? Okay. Interesting. On a lighter note, we all have a tendency to go for all of the above when that option is there in the MCQs. You can even choose B and C. We can choose A and B. I'm just telling you, or A, B. Oh, not A, B, and C. It can be A and B, or B and C, or A and C, or D. Let's address option C, keeping water and concrete under vacuum. Obviously, because of vacuum, water will get into the concrete. So it's as easy as that. It ensures better penetration of water into the concrete. So definitely there is option C. Now, let's move to the correct answer. The correct answer is B and C. It's not D. Why? Because if you know what boiling of water does to the water, it reduces the surface tension of the water. So, when you boil the water, it reduces the surface tension of water, which makes the water get into the concrete easily. So, if that is true, then A cannot be true. A says increasing the surface tension of water. So, A cannot be true. It can, the only possibility is B and C. D cannot be the thing because A is false. Okay. So A is increasing the surface tension of water. Unless you are decreasing the surface tension of water, water will not penetrate into the concrete faster rate. Boiling the water reduces the surface tension. So as a result of which the water penetrates into the concrete. Keeping the water and concrete under vacuum also is an accelerated way with which you can ensure that water easily gets into the concrete microstructure. Okay, so the correct answer is B and C. Okay, moving on to the next question. Choose the correct statements corresponding to the Venner 4 probe resistivity test. So, this is an electrical measurement of concrete durability. So, you can look into the screen, maybe not into the chat box because that has become very clumsy. So, in option A, current is applied between the inner electrodes and voltage is measured across outer electrodes. Option B, current is applied between the outer electrodes, voltage is measured between the inner electrodes. Now, C, voltage is applied between the inner electrodes and the current is measured across outer electrodes. Option D, voltage is applied between the outer electrodes and the current is measured across the inner electrodes. So it basically focuses on where what is provided and where what is measured. So current and voltage are the only two participants. Are we providing current or voltage? And are we providing it in the inner electrodes or in the outer electrodes? So these are the only two things. Okay. Actually, this question is easy. Apart from that, it looks very clumsy. Okay. Thank you for your response. I think it's a good number of responses. So let's move to the correct answer. So this is a figure. So here we apply the current in the outer electrodes, between the outer electrodes, and we measure what is the potential between the inner electrodes. So the correct option is B, as most of you have rightly told. So we give the current between the outer electrodes and we measure what is the potential between the inner electrodes. Here M and N. Okay, or P1 and P2. I hope that is clear. And let's move to the next one. The conductivity obtained by the RCPT, that is a rapid chloride penetration test of geopolymer concrete, is dash the regular OPC concrete. Lesser than, more than, or same as. So it's about the conductivity of geopolymer concrete and also the conductivity of regular OPC concrete. Everything else kept the same. What will be the comparison of conductivity? If it is a geopolymer concrete and a regular OPC concrete, the conductivity of geopolymer concrete will be lesser than, more than, or same as that of the regular OPC. You have to keep in mind that conductivity is not something which we desire, because conductivity is high means that there is more permeability or more charges can pass through. So, yeah. Okay. Should I wait for some more time? Okay, I'm going to the answer. So the okay. Okay. So the correct answer is more than, which is option B, that is the conductivity of the RCPT test of geopolymer concrete. So that conductivity of geopolymer will be more than the conductivity of regular OPC concrete, because geopolymer concrete, as you right know, it is containing more number of alkali oxides and alkali ions. So because of this presence of alkalis, these ions, the conductivity is found to be much higher than that of the regular OPC concrete. But that doesn't mean that geopolymer concrete performance is lower than that of the OPC concrete performance. So there is a contradiction over there. But generally, if you compare the conductivity, geopolymer concrete will show a higher conductivity. Now, moving on to the next question. The depth of chloride penetration in concrete specimens is determined by using the chemical silver chloride, silver nitrate, sodium nitrate, or magnesium nitrate. So, chloride penetration is very critical, because in the beginning I have told about the corrosion of steel reinforcements, and chloride induced corrosion is one of the major threats which are faced by most of the reinforced cement concrete buildings. So we need to know the depth of chloride penetration at a particular time period, or we can compare the depth of chloride penetration between different compositions of concrete. So, in order to understand the depth of chloride penetration, we can use a chemical. We can cast the concrete, expose it to chlorides, and then we can cut it and use this particular chemical to assess how much the chloride penetration has occurred. So, which chemical is used to understand the depth of chloride penetration? Is it silver chloride, or silver nitrate, or sodium nitrate, or magnesium nitrate? Okay, so I think that's it. Let's move to the correct answer. The correct answer is B, as most of you have rightly told. So, what happens is we can use silver nitrate, we can spray it onto the concrete cut surface. So, when if the chloride is penetrating in this direction, just cut it and then spray it, so that you can see that wherever the chloride is present, silver nitrate combines with that chloride to form silver chloride. So silver chloride has a white color. So because of the color difference, you can see that this much depth of concrete has been penetrated by the chlorides. So silver nitrate is the correct answer, and silver chloride is the end product. Okay, moving on to the next question. Sulfate resistant cement has low C3A content, high C3A content, low C3S content, or high C3S content. So choose the option which is very significant for the sulfate resistant cement. C3S, C3A gives the hardening, C3S for high early strength. So what is there for sulfate resistance? Okay, so let's move to the answer. Correct answer is A, as you have told correctly. So what happens is that if you have a low C3A content, then the ettringite, the formation of ettringite will be stabilized. It will not further react and form monosulfate and later on come back as a ettringite during the time of sulfate attack. What happens is if the monosulfate is a stable phase, then there's a high chance that ettringite can form at a later stage, which is known as a delayed ettringite formation, and this can cause expansion, and this is very detrimental for the concrete. So sulfate attack can occur if monosulfate is the main major phase. Suppose we are not allowing the formation of monosulfate only, we are stabilizing the ettringite formation so that it will not convert to monosulfate by reacting with C3A. So we are reducing the availability of C3A so that ettringite will be more stabilized there. Only if it converts to monosulfate, it can convert back to ettringite. So initially itself, we just cut that reaction there, stop the reaction there. We are telling that no, ettringite has to be stabilized. So for that, we have to have a low C3A content. So the correct answer is A. So moving on to the next question. Thaumasite is the phase with less binding capacity than CSH. So this is also the formation of thaumasite. Thaumasite can also weaken the concrete because instead of CSH, if it is thaumasite which is forming, then it will not bind properly, bind the particles together. So, what is thaumasite composed of? Calcium silicate phosphate hydrate, calcium silicate sulfate hydrate, calcium silicate carbonate hydrate, or calcium silicate nitrate hydrate. Okay. Anyone else? Okay. I think that is enough amount of time. Okay, everyone went for B, calcium silicate sulfate hydrate, but thaumasite is calcium silicate carbonate hydrate. Okay, this is finally one answer. Yeah. So this is calcium silicate carbonate hydrate, that is thaumasite. So this carbonate can get into CSH maybe because of limestones present or from water carbonates can get in. So that is a phase which is having a lesser binding capacity than that of CSH. So I think, yeah, that's all for
Ma'am,
today.
when sir was explaining, ma'am, sir told that it is calcium, silicate, and sulfate because he wrote on that uh,
Did he?
this thing, ma'am, projector also, that is C dot S dot S bar, that is sulfate, and then C bar, carbonate.
Yes.
One slide is there, ma'am. Other forms of sulfate attack, ma'am. That is the slide heading, ma'am.
Okay, okay. So then you are telling it is B and C.
Ha, ma'am. Actually, that's why I got confused because hydrate is not there. When sir was explaining, he said calcium, silicate, then he wrote S bar, that is sulfate,
Okay,
and
okay,
then
okay.
C bar, that is carbonate.
Okay, okay, okay. Okay, fine. So the answer will be B and C.
Yes, ma'am.
Okay, okay. Thank you. Okay, so I'll just correct it here itself, maybe. Okay, I hope that is done. Okay, so that's all for today. I hope screen share is closed. Yes. Okay.